bit of introduction while he's setting up. So next is Yassine Ben Emin from Siemens PDA. He's a product architect for formal tools at Siemens and responsible for formal technology release planning and feature development.
Yeah. Right.
Yes.
Thank you for the introduction. I'm going to talk about FPGA verification. And I'm specifically going to talk about how you can leverage equivalence checking to provide design and verification assurance, especially in the context of security and safety. Anybody here does FPGAs for things like ISO 26262 or DO254? All right, okay, so you'll be familiar with some of these aspects that I'm going to talk about. Actually, the presentation that Marius just did is an excellent segue to my presentation, because Marius presented a simulation-based framework for making sure that an FPGA is functionally correct, and he's talked about regressions. He's talked about how you set up the regression, the efforts required, and the type of regressions that you have to have and maintain, and so on. All of those things are well understood. I'm going to provide an alternative which goes further than that and provides another level of automation. So if this slide moves. Yay! Okay. And I don't know if anybody spotted you, this exact same number that Marius put on his slide. So yes, we can also report that 87% of FPGA design projects have non-trivial problems, non-trivial bugs, which means it takes a long time to try and figure out what the problem is. This is okay if you're doing an FPGA device that goes into a non-critical application. But at the moment you're doing stuff for medical or for aviation or anything else that requires safety, then any functional escapes will impact greatly the products. Essentially, failure is not an option if you're doing an FPGA device for relay, for example, or for medical. And so what's needed? Absolute assurance. How do you get to absolute assurance with FPGAs? And that's really what I'm going to talk about with equivalence checking. Just some market data so I can highlight and try and quantify how important this is. So if you actually look in the certification standards or the guidelines that these standards provide, for example, for A&D, if you look at DO254, DO254 will not specifically mention equivalence checking. However, for DoD, that's the US Department of Defense, the LOA, so that the level of assurance, they actually specifically mention equivalence checking. AFMAN gives strong hints to equivalence checking. Again, automotive, you may come across that. Industrial, you may come across it. Nuclear, again, not specifically mentioned as a requirement to do equivalence checking, but it talks about exhaustive testing and so on. And so they all are looking for some form of assurance when it either comes to security compliance. So not only do you want to check that the functionality is maintained through the implementation process, as you go through synthesis, as you go through placing routes, and all the way to bitstream generation, you want to make sure that there are no Trojans in the system. And as I said, if you've got a safety compliance, then you want to be able to demonstrate that. And we hear more and more in the industry, our customers are talking about evidence-based assurance. Whereas I think in many design and verification flows, it tends to be experience-based assurance. We've done it this way before and it worked, so it should still work. This is just the next revision of the design, so it's really not doing anything different, and it worked in practice, So we just changed the version of the value, for example, so there is no problem and so on. There is more and more requirement now for evidence-based assurance.
Mm.
And so this is the EDA solution that we provide. This verification all the way through to the bit stream gives you absolute assurance. And we actually do it in partnership with Graph Research, who provide this product. But let me start at the beginning of the verification flow. You've got your RTL, and you go through synthesis, and I'll talk about how we support Vanda, how we support several other device vendors. You get a net list, and then you do inflation route, and then from there you get a final net list, and you go through the bit stream. The bit that we provide is here. That's Questa-equivalent FPGA. As the name suggests, it's giving you assurance that two versions of the FPGA at different stages are exactly functionally the same. And then NVRETI PV bit provides a way of checking that the bit stream that you got does indeed implement the devices that are present in the netlist. Okay. We believe this is a unique offering to go all the way from RTL to bit stream. And of course, we couldn't have done it without our partner in the US, NVRETI. NVRETI and Graph Research have been working in this area for a very long time with some of the key A&D companies in the US. Some examples of security and safety concerns that we deal with and that this targets. A security concern could be like a hardware Trojan horse. So an example here, something that leaks encryption key using some clever encoding scheme, it usually gets inserted into the physical netlist. You can catch this with Questa-equivalent FPGA. That's the Siemens EDA software. You also have some other types of Trojan horses, like this one here, which actually weakens the crypto engines, and it enables man-in-the-middle type of attacks. This kind of thing gets inserted into the bit stream itself. We can't catch this using equivalence checking. However, NVRETI PV bits can do that because they can check the two stream, one that they've inferred and the one that was generated. Okay, and so yeah, this is the flow, and this is where we either deploy Questa-equivalent functional verification or for bit stream generation. It's a smaller audience than before. I'm quite happy to take questions as I go along. Okay, and like the previous presentation, you can do this with simulation. You can actually write vectors, and you can put a regression in place. So what's different in here? Well, it's exhaustive, and you don't have to write the vectors. So a very, very small piece of RTL, 3 inputs. If you really want to be exhaustive, you need to write 2 to the power of 3 possible inputs, and you need to make sure that you simulate deep enough, depending on how many flops you've got, how many cycles you've got in the design. And so you apply that to the RTL, you apply that to the netlist, and you check the outputs. So that's what your regression would be doing, really, to check that stuff is equivalent. Even if you did this, you won't be able to catch things like Trojan horses, because they are usually triggered using something very difficult to detect. That's the whole point. And so, yeah, that simulation, logical equivalence checking basically automates this. It's using formal methods to do this. I don't know how many of you also have a background in ASIC design and verification. In ASIC design and verification, this is very well known. But in FPGA, very, very few FPGAs tend to do equivalence checking for various reasons, which I haven't got time to go through in this session. But yeah, it is available. Can you just use a standard LEC, logical equivalence checking? You can try, the trick with synthesis for FPGAs is that, unlike RTO synthesis for ASICs, it's much more of a macro-based type of synthesis, and it's much more of a behavioral, or at least it uses some behavioral synthesis algorithms. So typically using just LEC, it's very difficult to achieve equivalence checking. You really need to use what's called sequential equivalence checking. And that's the key in making Questa equivalent FPGA work. It's actually clever in that it uses a combination of both. If you can get away using LEC, you do it. If you can't, then you deploy sequential equivalence checking. Now, that's some of the optimizations that would break LEC out of the box, which you'll have to deal with. There's a lot of clever stuff that you have to do to be able to sort of reverse engineer. You need to understand how the design was modified sequentially to work out whether things are equivalent or not. And for that, you need a partnership with the device providers, the likes of AMD, the likes of Lattice, and so on. If we find that the designs aren't equivalent, then of course you'd expect us to give you a waveform-like counterexample, and that's exactly what we do. So the same thing as with simulation, here we can give you a reference design, a golden design, and the implementation or revised version, and we can tell you this is the difference between the two. And there is schematic support as well, so we can highlight where in the schematic the difference is. If you need certification, this software is certified for ISO 26262, and you can get the qualification straight from TUV. Look for Questa Equivalence FPGA, you get that.
Certified for 61508 as well.
I need to check on that. Yeah, I need to check on that. These are the vendors that we work very closely with. AMD, Altera, and Microchip. They actually recommend us for as an equivalence checking tool. That not only do they recommend us for their clients or our mutual clients, they actually use this for their own QA because they're developing synthesis tools and they're turning on optimizations and so on. They use this as their internal QA tool. So AMD keep us very, very busy. Altera keep us very, very busy, and Microchip and so on. And there's different synthesis tools. There is some support for Simplify as well, if any of you are using Simplify. And some devices are much better supported than others. So if you're interested in this, let me know and I can give you a list. I think the list will be on the website already. Last but not least, I don't know how I'm doing for time. How about the last part of the flow, which is verifying the final net list versus the bits stream. And graphics surgeons do some good marketing for this. Verify the bits that fly. Here is what's actually, I'm going to jump to this slide straight away because it explains very well how it works. This is the physical net list that you get. So you do a checkpoint in the tool and it spits out this final net list. And the final net list is essentially instantiations of devices and where they live on the FPGA, their location. The bit stream also has information that says similar thing. So it says there is an oscillator at this location. And really, this is what the check-in that NVRate FPGA bit do. They get a list from here, they get a list from there, and they cross-check. And if there's anything extra, they'll tell you that is extra, so that can identify treasures that were inserted, or if there's anything different, they'll tell you that there is something not quite right that's different between the two. And PVBit itself is not, you really have to speak to graph research, so it's not using formal methods, but it's exhaustive because it's building a checklist between the two. So this is very quick to run. You're talking 10 minutes, 15 minutes, because it's doing equivalence checking, however, that's checking functionality. And so your runtimes could vary. We had a customer present a success story a year ago, and they had a device, a designing device, Vertex, I can't remember which one. But anyway, they have a nuclear application where they basically moved to a different technology, a different device, and different software version. And they needed absolute assurance that it's exactly functionally the same. It only takes them 2 hours to run the equivalence. But we also have others who have much higher utilizations, and it takes them 2 days to run the equivalence. But I'd like to think that the value proposition is uncontestable compared to simulation, where you probably have, first of all, to invest the effort in putting the regression, make sure that it's sufficient, and depending on how many licensed simulators, we're quite happy for you to buy more licenses for the simulator. That depends on that and the machine and the compute power that you've got. It may actually take just as long. So yeah, I presented how you can leverage equivalence checking from RTL all the way down to bitstream. We believe this provides a unique solution, particularly in partnership with NVRET APV.
Questions?
Say if you wanted to make a change for a design, say you had a PLD or some kind of reprogrammable FPGA, and you had, or an SoC, and you had multiple different logical functional blocks inside of that, and you wanted to change just one of them, but you wanted to leave the functionality of the others exactly the same, and verify that your change made to the one block wouldn't have any adverse effects on the other ones. Would this tool help with anything like that, or would it essentially everything has to be exactly the same?
It does do already some automatic partitioning within the tool, but you also have access to scripting that can do hierarchical partitioning, so you can black box certain things, or you simply, you don't have to do all of the verification at the top level, at the device level. This can be part of a design and verification flow. We've got customers that do this as part of a continuous integration. So at the block level, they check that the synthesis doesn't break any functionality, especially if they're inserting things like power, optimizations, anything, safety mechanism, or anything like that. They don't have to run, they don't have to wait until the top level. So yes, there is support for partitioning both automatic and manual using hierarchical information.
So what would the output look like then if you were to do that from the tool?
But the output from equivalence checking is pass or fail.
Yeah,
that's what it is. Yeah, and so yeah, that's the result. It's pass fail.
Yeah.
So the bitstream checker, would that pass or fail if it's functionally the same, but it's physically moved registers about and changed the routing?
No, so with the bitstream, that's relying on the location on the device and what type of device it is. Yeah.
So it's actually looking at if it's a different placement, it will.
It's not.
Fail.
Yes. Yeah. It's not. And it has to do this, and nobody asked me the question. It has to do this without reverse engineering, because first of all, you couldn't, without missing information, with bitstream generation, you just don't know how you generate a bitstream. You don't have the algorithms for that. That's why it's coming at it from different ways. It's not possible to reverse engineer where the FPGA is. Exactly.
Thank you.
Thank you.
Thank you.
That's the FPGA session finished for today. This session.
Oh yes, sorry. Yeah, finished for you. Yeah.
Thank you.
I'm gonna. Pretty job.